Okay, hello everyone. Welcome to LICD lecture 41G. There are four topics which we will be discussing today. First one is second order active KRC bandpass filter. We'll analyze the circuit, see its frequency response, and we'll verify some values with LTspice simulation. Then we'll see the generalized transfer function. From there, we'll derive the cutoff frequency F0 and the quality factor for the same. And we will see one more design of the second order active KRC bandpass filter. And next we'll go to the band reject KRC filter or a notch filter. We'll analyze the circuit and its operation and also build up its frequency response. Lastly, we will design a notch filter, which will include the design steps as well as the LTspice verification of the design values. Okay, so let us begin with the lecture. So let me put this in full screen mode. Okay, yeah. So this is my second order bandpass filter. The circuit is exactly more or less similar. Only thing is that the RNC components are inversely placed over here. So in case of it's a combination of the low pass and a high pass response basically. Okay, so here we have only additional R3 element which is present from the output to this terminal. Okay, and here the first capacitor is grounded and the second R2 resistor is also grounded. So that's the difference between the earlier filters which we have discussed, that is low pass and high pass. It also consisting of two RC elements, but here additionally there is a R3 resistor which is present over here. Okay, so here we have RA RB as usual. So this is again the opamp is in the non-inverting configuration. Input is being applied to the resistor R1 C1 combination, followed by R2 C2, which is connected to the non-inverting input terminal of the opamp. And R3 is the additional resistor which is necessary for a bandpass KRC filter. Okay, so the observations are the above circuit consists of an RC stage followed by a CR stage to get a bandpass response and a gain block to provide a positive feedback via R3 register. Okay, thus feedback is designed to improve the response near omega by omega naught, which is equal to 1. Okay, so this is my frequency response for my band pass second order band pass filter. As you can see very clearly, the band of frequencies between omega L and omega H are passed, whereas all other frequencies, that is frequencies below omega L and the frequencies above omega H, are rejected. Where HOBP over here is my resonant gain, or my you can say the band pass gain, and omega naught is the peak or the resonant frequency. Okay, so this point is clear. So all the frequencies below omega L and above omega H are rejected at the rate of 20 dB per decade. And my bandwidth of this band pass filter is given by omega H minus omega L. Now let us see the derivation for this. So actually I will just be describing, I will not be deriving entire steps. I'll be just keeping it static for 5 seconds. You can jot it down in your notebook. You can pause the video and you can try it out yourself, because the more important thing, that is the design, is focus over here. So for a derivation for F0 and omega and quality factor, we will use admittances. So here various capacitors and resistors are used as admittances, and here we can apply the KCL and KCL at V1 and V2, and then we'll find the relation between V0 and V1. Okay, here the output voltage is given by V out is equal to 1 plus RA upon RB into V2, because the V2 is the input to the non-inverting terminal. So this amplifier, this circuit is behaving as a non-inverting amplifier basically, in terms of V2 being the input. So here K is 1 plus RA upon RB. So V0 will be K into V2. Now we have to determine the relation between V0 and V in. So for that we apply KCL at V1. So you can have a look at it. Okay, I am not describing it. So you can have a look at the diagram as well as this. So I will describe only the first step. Rest of the steps we can follow it up. So KCL at V1 gives us all our outgoing currents. So V1 minus Vi into Y1, V1 minus V2 into Y2, V1 into Y3 plus V1 minus V0 into Y5. So you get this huge expression. Over here we substitute instead of V2 uh, in terms of V0. So we get equation number 1. In equation number 1 we also have V1 present. So next step we have to apply the KCL at V2. So KCL at V2 gives us V2 minus V1 into Y2, then V2 into Y2, Y4 is equal to 0. So that's what we get. V2 minus V1 into Y2, V plus V2, Y4 is equal to 0. So from here we get the relation of V1 in terms of V0. We substitute that in equation number 1, okay, and we rearrange this term such that the transfer function will only contain V0 and V in. So H of S, that is equation number 3, is my transfer function, generalized transfer function in terms of admittances. Now for a bandpass filter, we substitute these values in terms of component. So Y1 will be 1 upon R1, Y2 will be SC2, Y3 will be SC1, Y4 will be 1 upon R2, and Y5 will be 1 upon R3. You can check it out, cross check these values with the actual diagram. So with this diagram as well as this diagram, you can compare it, you will get those numbers, you will get those results. And in this, if we consider the equal component design to simplify the mathematics, so what we will do is we substitute R1 equal to R2 equal to R3 equal to R, and C1 equal to C2 equal to C. So then your admittances Y1, Y4 and Y5 will be same, equal to 1 upon R, and Y2 and Y3 will be also be same, which will be S into C. So if we substitute that in the general expression given in equation number 3, you will get the following result. Okay, so H of S will be this huge term. So here we'll divide and multiply by R square. Finally, after slight simplification, you will get H of S as K by 2 into SRC divided by S square R square C square divided by 2 plus SRC into 4 minus K divided by 2 plus 1. So we substitute S equal to J omega so that we find the transfer function in frequency domain. So H of J omega will be K by 2 into J omega RC divided by 1 minus omega square R square C square divided by 2 plus J omega RC into 4 minus K divided by 2. So this is our equation number 4. So this equation number 4 will compare with the standard form of bandpass filter. Let us check the standard form. So these are standard second order responses. Let us check the bandpass response. This is high pass response. This is bandpass response. As you can see over here, we have in the expression HOBP. So HOBP is the resonant gain, and over here, right? So HOBP into J omega upon omega naught into Q divided by 1 minus omega upon omega naught square plus J omega upon omega naught divided by Q. So that's the standard form of a bandpass filter. Okay, the standard form of all bandpass second order bandpass filter is H of J omega. So this is your H of J omega which is given by. So hence we compare this equation number 4 which we got over here. Equation number 4, if it is compared with equation number 5, we can get these terms 1 upon omega square. So let me just reduce it. Okay, so over here 1 upon omega square will be given by R square C square in, by 2. So omega naught will be, omega square will be 2 upon RC square. So omega naught will be square root of 2 divided by RC. So F naught will be square root of 2 divided by 2 pi RC. So this is the resonant or the center frequency of the second order bandpass filter. Similarly, if we do the further comparison, you will get 1 upon omega 0 Q will be equal to RC into 4 minus K divided by 2. So let us compare this. Yeah, this term if you compare, J omega is present. So 1 upon omega naught Q will be equal to RC into 4 minus K divided by 2. That's what we get over here. So over here, if you write Q in terms of omega naught, so it will be 2. If you simplify this further, you will get Q is equal to 2 times divided by RC into 4 minus K into omega naught, and omega naught is square root of 2 into RC. So over here, we get the quality factor for a bandpass filter, which is given by the equation square root of 2 divided by 4 minus K. Now, one more term is there. So we need to determine the value of, HOBP. So from the standard form, HOBP into j omega upon omega naught q will be equal to k by 2 j omega RC. So that's the value which we are getting. So HOBP divided by omega naught into q will be equal to k by 2 RC. So we substitute the values of omega naught and q over here, and after simplification, your passband gain or the resonant gain, the band pass filter is given by HOBP will be equal to k divided by 4 minus k. Okay. So for a band pass filter, your quality factor is given by omega naught upon bandwidth. So your quality factor over here is given by f naught divided by bandwidth, which is omega h minus omega h. Now let us see the design now. So we'll design a second order band pass filter with a cutoff frequency of 1 kilohertz and a bandwidth of 100 hertz. Okay, and also find the resonant gain. So this is the design statement given. We will adopt a equal component approach. So in the equal component design approach, R1 will be equal to R2 will be equal to R, and C1 will be equal to C2 will be equal to C. So over here, and RA and RB values are also to be found out. So all the unknown values of resistors and capacitors we have to find in this design. So the formulas are as given as follows. HOBP is K upon 4 minus K. Omega naught is root 2 divided by RC. Q is root 2 divided by 4 minus K. Okay. So now let us go proceed further. So for a band pass filter, the frequency is cutoff frequency, resonant frequency is root 2 divided by 2 pi RC, which is equal to 1 kilohertz given. So let us consider the value of C as 10 nanofarad. So C1 will be equal to C2 will be equal to 10 nanofarad. Then we can find the value of R as root 2 divided by 2 pi F naught. F naught is given as 1K and C is 10 nano. So you'll get a number close to 22.5. We can take a standard value 24 kilo ohms standard. Now we know the quality factor is given by the formula F naught divided by bandwidth. Here the bandwidth is given as 100 hertz and F naught is 1K. So Q will be 1 kilohertz divided by 100 hertz, which will be 10. So once Q is 10, we can easily find reverse calculate K. So K will be given by Q is given by root 2 times root 2 divided by 4 minus K, which is equal to 10. So K will be given by 4 minus root 2 upon Q. So you substitute over here, you get the value of K as 3.858. So these are the values of K which you get. So K over here is 3.858. So K will be equal to 1 plus RA upon RB. So RA upon RB will be 2.858. So that means RA will be 2.858 times RB. So let the value of RB as 10K. So value of RA will be 28.58 kilo ohms. So we can substitute the standard value close to around 27 kilo ohm standard value. Okay. Now the last thing is we need to also find the resonant gain. So or the passband gain. So resonant gain is given by K upon 4 minus K. K is 3.858, which we have evaluated over here. Yeah. So the passband gain will be K divided by 4 minus K. So that will come out to be 27.28. That number will be 27.28. Okay. So here is my design circuit with all the values R3, RA, RB, C2, C1, R1, R2. Okay. So this is designed for a band pass second order band pass filter for a cutoff for the resonant frequency of 1 kilohertz and bandwidth of 100 hertz. Okay. So let us check out that this design in LTspice now. Okay, let me open the LTspice window and let me close this and open the bandpass filter design. Okay, bandpass filter equal component design. Okay, here is the circuit. So we have taken the exact value of resistors over here. Okay, so here we have it. RA was 28.58 kilo ohms. RB is 10 kilo ohms. Then the value of R was 22.5 kilo ohms, and all the R's, R1, R2, and R3. And the value of all the capacitors were 10 nanofarad. So here it is. So I've taken the exact values because we have the flexibility in LTspice to do so. So now let's check out the frequency response. So this is my circuit I have built up in LTspice. So you all can also similarly build up and check the response. I have used opamp op07. So we'll go to simulate, click on run, and let's check the output. Yeah. So here we have it. So here I have my bandpass response, right? Second order bandpass response, as we have discussed in the theory, it will exactly look like this. So let me show it to you. Yeah, here it is. See, this is what we have discussed, and this is what we are getting over here. Exactly the same. Now, let's check everything over here one by one. Let us go back to the design values. Okay, so these are the design values. So first of all, the cutoff frequency, we'll check the resonant frequency is designed for around how much is the value of the cutoff frequency? 1 kilohertz. Okay, so it's designed for 1 kilohertz, and let's substitute the values as per the design. So let's say I have 24k. I think it is 27k over here. Yeah, let us check it out as, let us substitute as 27k standard values and check. Here it will be 24k. Here also it will be 24k, and finally here also 24k. Okay, now let's check out with the design. We have taken the standard value of resistors, and I think it won't matter that much. Let me just undo all the values. So what I was trying to do was I was checking whether the cutoff frequency range is properly coming or no. So over here, the highest frequency will be my resonant gain. So at 1 kilohertz, I'm getting over here. So it's slightly less, but it's nevertheless. Let's check that number once. Okay, it's definitely behaving as a bandpass filter, as you can see very clearly. Some frequencies are getting, as you can see, it's a range of frequencies, and the range will be 100 hertz basically. So the highest value over here, which we are getting, 1k, we are getting over here. You know, 1 kilohertz we are getting over here, but we should get that at the maximum value. That is over here. That's fine. That's not a problem. Not a problem. So we can check the value now. Okay. So the highest value of the HOBP will be 27.28. So we can take 20 log to the base 10, 27.28. Okay, so that's fine. That we will check it later. But the nature of the response is quite same. Maybe the cutoff frequency, the resonant frequency is not coming at the peak, it's coming little bit aside. So that's fine. And we have to go 3 dB down and check out the values for the range of bandwidth. Okay, so it is providing a, it should provide a cutoff frequency of 1 kilohertz and a bandwidth of 100 hertz, but I think it's providing a bandwidth slightly different than that. That's okay, but the nature of the response is absolutely correct. Fine. So here was the frequency response of a KRC bandpass filter, and this was the design, equal component design. Equal component design will always give some shift in the, slight shift in the frequency, because there are so many resistors and capacitors connected. So they're bound to happen some frequency shift change. So 1 kilohertz is coming over here. Okay, at around minus 3 dB, you are getting around 1.01. Okay, highest value over here is 1.3. So if you come 3 dB down, you will get this range of frequencies. It's fine. I think the nature of the response is correct. We should not bother too much about the cutoff frequency. Okay, now let's go to the next topic. So the next topic is the band reject KRC filter, or it is also called as active twin filter or notch filter. So notch filters are used when it is necessary to remove a single frequency from a signal. Okay, so this is our band, our twin T network, or your opamp is connected in the non-inverting mode basically, and it has a twin T. So you can see C, and this R by 2 forms a T network, and this RN2C forms the inverted T network. So that's why it is called as a twin T network. And the positive feedback is given via this part, and the negative feedback is given via this part. So opamp is working in the non-inverting mode with input as V plus, okay, and the gain as 1 plus RA upon RB. That's definite. So how does 20 circuit works? So the opamp is in the let me reduce this slightly. So opamp is in the non-inverting mode. That's why output is given by 1 plus RA upon RB into V plus, which will be K times V plus. So output will be K times V plus actually. Now, this is the frequency response of a notch filter. So as you can see, it's removing only one frequency, whereas the bandwidth is quite low. So it has one stop band and two pass bands. So HON is my stop band gain, basically, and this is my notch frequency. So you will remove only one frequency from all the frequencies. Okay, so this is the typical response, frequency response of a notch filter, and this F is called as the notch frequency. Okay, so how does the working goes? I think I have to open one more PDF of this. Let me do that quickly. Okay, I'll paste one PDF over here, and I have to open it because the circuit diagram is required for explanation. Will be required actually. Okay, I can place this over here, and second PDF I will open it over here. Okay, that's fine now. So we have got both the PDFs, same PDFs only, but for explanation I have to keep one PDF open for the diagram purpose. Okay, I'll quickly go to the 20 network. Okay, so this is my circuit diagram. So we'll concentrate on this circuit diagram and limit answers to this. Okay, and on the left hand side, I'll describe the theory behind it. Okay, so let's see the working. So the circuit will consist of twin T network and a gain block to provide the positive feedback via the top capacitance 2C. So the twin T network provides alternate forward paths through which the Vin can reach the amplifier input. Okay, so we have a low frequency part given by RR, and we have a high frequency part given by CC. Okay, so let's consider this. At low frequencies, the reactance offered by the capacitance is high, correct? Because XC reactance and the frequency are inversely proportional. So if the frequency is very low, the reactance is very high. So the capacitors will behave as an open circuit. So all the capacitors will behave as an open circuit, but input will reach the amplifier via R and R, via this network R and R, because resistor have no effect on the frequency. Now, at higher frequencies, the reactance offered by the capacitances becomes very low. So capacitors behaves as a short circuit. So the input reaches the amplifier. Now we know that if you have a resistor and a short circuit, the short circuit part will be preferred because the current always prefers the least resistance part. So at a higher frequency, this capacitors will behave as a short circuit, and the input signal will reach to the input terminal of your op-amp via this capacitor, two capacitors C and C. At intermediate frequencies, maybe at some particular intermediate frequency, the two parts provide opposite phase angle. Okay, so it might happen that this part and this part phase angle will cancel out. So indicating the tendency that the two forward signals cancel out each other at the amplifier input. So in that particular case, no amplifier input will reach the input terminal of your op-amp. Okay, so that means it will reject the notch frequency, that is the intermediate frequency. So we thus anticipate a notch response as observed in the frequency response of notch filter. So that's why we get this kind of a notch response, wherein this response will indicate that it will remove the notch frequency from the circuit. Okay, so if we analyze AC analysis of the circuit gives the transfer function in the following form. We have not derived it. One can derive on the similar manner on the lines of low pass, high pass, and band pass response. So here I'm directly writing the result. So this is the standard notch response equation. So I'll show it to you. Notch filter. So here we have a notch response. HON into 1 minus omega upon omega naught square divided by 1 minus omega upon omega naught square plus j omega upon omega naught into q. So that's the equations which we are getting. And while deriving, when you derive it, you will get the values of HON as K, which is the actually it's a stop band gain. We can call it is a pass band gain. Sorry, and omega naught is the notch frequency, which is 1 upon RC. Q is given by 1 upon 4 in minus 2Q, 2K. Q is given by 1 divided by 4 minus 2K, where F naught will be 1 upon 2 pi RC. Over here, the K value is 1 plus RA upon RB, and also the quality factor is also given by the formula F naught upon bandwidth. So from the frequency response, it is clear that now where is the frequency response over here? Yeah, here. So from the frequency response, it is clear that the circuit will reject the frequency around uh, f equal to fn basically, or omega equal to omega naught, with a maximum attenuation. Okay, whereas it will pass all other frequencies with the maximum passband gain. So that is very, very clear. Okay, so let's go to the final design for this online session, online lecture. So design a notch filter having f naught as 60 hertz and a bandwidth of 5 hertz. Okay, so the very first thing is the quality factor. So quality factor is given by f naught divided by bandwidth. So f naught is basically a notch frequency over here. It is 60 divided by bandwidth is 5. So quality factor is 12. Now f naught is also given by 1 upon 2 pi RC, that is 60 hertz. So from here, let us say that the value of C is 100 nanofarad. So 2C will be 200 nanofarad. Okay. So we can calculate the value of R. It comes out to be 26.526 kilo ohms. We can take the nearby standard as 27 kilo ohms. So the value of Q is given, formula of Q is given by 1 upon 4 minus 2K. So we can find the value of K from here. So over here, if we find the value of K, that will be 4 minus, I think, let us check it out first. So 2K will be equal to, yeah. So 2K will be, 4 minus 2K will be equal to 1 upon Q. Actually, this should be, the whole should be divided by 2 actually, but that's fine. I think there is some mistake in this step. Q, if I substitute the value, let me put the values in the calculator and check. So Q is around 12. So Q, let me put the values in the calculator. Q is around 12 divided by 1 divided by 4 minus 2 into, let me substitute this value now. 12 is equal to, so okay, so 4 minus 2K, let me open the annotation. So let us check it out now. So it will be 4 minus 2K will be equal to 1 divided by Q. Correct? So what will be K? So actually I can write it as 2K will be equal to 4 minus 1 divided by Q. Okay, yeah, I am right. So K will be equal to this term, entire term, whatever I'm getting, divided by 2. Okay, so K will be equal to half of 4 minus 1 upon Q. So that's the value of Q actually. Okay, so that's the correct answer. I think I made a mistake over here. So we can correct it. So it will be 4 minus 1 divided by, okay, 1 divided by 12, fine, divided by 2. So your value of K is coming out to be, let me just write it over here. So actually it is 40, just a second, 4 divided by 1, 4 minus 1 divided by 12. So that is divided by 2. Yeah. Okay. The formula is wrong, but the calculations are correct. Okay. So over here, this is actually taken as into half only. I have just that it is not written it over here. So actually this is multiplied by half only. So this is multiplied by 0.5. Okay. This is multiplied by 0.5. So if you put it in a calculator, this will be 2 minus 1 divided by 6. That will be, okay. So 4, let me just check it once more. 4 minus 1 divided by 12, and that multiplied by 0.5. Yeah, the answer is correct. Yeah, answer is correct, but only your half sign is missing. So please add that half sign over here in this. Okay. Now let me close the annotation. Okay, so K will be 1 plus RA upon RB, 47 upon 24, which will be equal to RA RB is 23 divided by 24. So let the value of RA will be 10 kilo ohms. Similarly, the RB will be 10 kilo ohms. So RA will come out to be 9.53 kilo ohms. So let's consider the nearby value of 9.5 kilo ohms standard. I think 9.5 kilo ohms is not a standard. You can consider 9.1 kilo ohms as a standard value. So nevertheless, we'll substitute the same value in LTspice actually. So your design circuit will look like this. Okay. Now let's quickly simulate this, because this was R and R, all R's were same, and this was R by 2. So this will be half of this 27 kilo ohms, and this will be twice C. So this will be 200 nanofarad. Okay, so let's simulate this notch filter, 60 hertz notch filter. Okay, let me close this and let me open a circuit for a notch filter, band reject KRC filter. Basically, okay, so this is the response over here. Let me just check the value. So this is the 20 network 2C. This will be 100 nanofarad. This will be 200 nanofarad. This will be around 27. I told you I've taken the exact values, not the standard values. And over here we have it as RA and RB 9.53 and 10K. Okay, so the design is absolutely correct. Now let's check this value, whether it's give a notch response or no. Yeah. So it's giving perfectly well, good results over here. As you can see, clearly see, it's rejecting a unique frequency. Now let's check what is that frequency. It should be close to 60 hertz. So let me magnify this a little. Okay. So if I place this down, I'm getting 63 hertz. Okay. Instead of 60 hertz, I'm getting the notch frequency at 63 hertz. That's absolutely fine. And this is how we will get a proper, response. Notch response will be 63.09 hertz, and we have designed it for 60 hertz. So that's quite close. Even if you tune your components a little more closer, you will get a more tighter control over the frequency. Okay. And the passband gain, well, one can check that also. So over here it was around 47 divided by 24, 20 log of that. Okay, so somewhere close to, let's see, 5.83 we were getting it, but here the passband gain will be 5.8 dB. So instead of 5.83, we are getting 5.8 dB as the passband gain, and with a notch frequency of 63.09 hertz. Okay. Okay, and if I come down by let's say 5.88 dB, right? So I have to come down to how much? 2.8 dB. Sorry, I have to come 3 dB down, right? So that's absolutely fine. We can come 70.7% of the highest value down also. So that will give me around yeah. So your notch frequency will be close to 63 hertz, and the passband gain is 5.8 dB. So that's enough to calculate this. Evaluate this band reject filter. Now, band reject filter is practically used in biomedical applications to remove the 50 hertz or a 60 hertz noise signal. Okay, so designing such a filter, giving such a response is also very, very important. And these are analog filters. So using your resistors, active elements as opamps, you can build this notch filters very, very easily with the correct values of R and C in the circuit. So this is also called as a twin T network, as you can see. Active twin T or band reject KRC filter. It has three names: band reject KRC filter, active twin T network, or notch filter. Okay, so this is how we see this topic. And we have completed. We have come to an end, and we have completed the notch frequency, no, notch filter also. And these were the results which we have got. Okay, so we got 63 hertz as the notch frequency, and the passband gain was 5.8 dB. Okay, so this is how we get the band reject filter or the notch filter frequency response. I think that's it for today's online session. Next time we'll start with a multiple feedback, filters, low pass filters, let's say. Okay, so that's it for today. Thank you for your time. Until we meet again next time. So till then, have a good day and thank you.